Alright, so we're going to pick up where we left off. Now we're actually going to take a whole bunch of data and we're going to organize it in a way that's actually useful to read. One of the tools that we use is called a frequency distribution table. So we have an example. Researchers are interested in determining the age at which adolescent males show the greatest rate of physical growth. Basically, in what year of their adolescent life do they grow the most inches in height? Okay? A random sample of 35 10-year-old boys is measured for height and remeasured each year until they reach the age of 18. The age of maximum yearly growth for each subject is as followed, and then we have this list of 35 different numbers. Each piece of data is called a data item. Okay, so I have 35 data items. I studied 35 different people. But a lot of those numbers repeat. Okay, so each unique value is called a data value. Okay, so I have a data value of 11. It occurs twice. Okay, so data items will repeat. That's just the number of items that you get. But each data value has to be unique. So I'm not going to have data values that repeat, or they will repeat, but I just say that I have the data value 11. Now, with this giant list of information, I want you to tell me, at what age do most boys achieve their maximum growth?
14.
14. How do you know? There's a lot of 14s. Are you 100% positive that's 14? No, that's a lot of information to sort through. Okay? Yeah, there's a lot of 14s, but there might be just as many or more 15s or 16s or 13s. Okay? So we need to organize the data in a way that makes it easier to read, to understand, and to interpret. Okay? So we're going to create a frequency distribution table. All right? It's a 2-column table. The first column, we're going to list all the data values. And then the second column, we're going to identify how many times those data values appear. So we'll start with the age of 10. How many times does the number 10 show up in this list? One time. Okay, that's the only data value. So it has a frequency of 1. It shows up one time. Then we go to 11. And we're going to run down the list and look to see how many times the number 11 shows up in that list. 2 times. So it has a frequency of 2. Alright, I'm going to cross those off because I've already counted those. And then we're going to go through and we'll see we've got a 12 here, 12 here, 12 there, 12 there, 12 there. 1, 2, 3, 4, 5 times. Continue doing that with 13 through 18. Fill in the rest of the chart. 13 through 18. How many times is 13 here? 17 and 18. Alright. How many 13s do I have?
You got 6.
You sure?
Yeah. I counted 7.
7.
Oh, that's right.
How many 14s?
9.
9. How many 15s?
6.
How many 16s? And 17s? 18s? Now, you should always double check this. Your frequency should add up to the total number that you had in your original list. They told us that this study was with 35 boys, so we should have a total sum of frequencies that equals 35. If it's off, then you need to go back and double check and make sure you didn't miss anything. Now, with this chart, it's a lot easier to see at what age do most boys achieve their maximum growth. 14. Why 14? The most frequent. 14 is when I have the most frequency, so the answer to that would be at age 14, when most boys achieve their maximum growth. Okay? Now, you may see this slide twice on yours. I think I kind of duplicated it. This one and the next one, I think they're on the twice, so just skip the extra one. Sometimes a frequency distribution table isn't going to be super helpful when we have too much variation in a data set, okay? If we don't have a lot of numbers that repeat. This is a list of statistics test scores for a class of 40 students. Not many of these values repeat. So a frequency distribution isn't going to be really useful for us because it's not going to create the same type of effect that this list here has. Okay? So what we can do is instead do a grouped frequency distribution where we create classes and group sets of numbers together. A standard grading scale does that automatically. Your typical grading scale within a school system is a grouped frequency distribution. You've got A's, which are 90 to 100, B's, 80 to 89, C's, 70 to 79. That is a group frequency, where you say that anyone that has a grade between a 70 and a 79 has a C for that course. Okay? And so it goes through all of our letters for A, B, C, D, and F. All right? So what we can do to better analyze this information to see how well this class did as a whole is we're going to create a grouped frequency distribution. Now, when we create classes, there's a couple different things. One, you want to try your best to get the classes to be the same size, as in the same number of data values in that range. And so we created classes from 40 to 49, 50 to 59, 60 to 69, 70 to 79, 80 to 89, 90 to 99. We could, if we wanted to, change this to be 100. None of these data values are 100, so it doesn't really matter. They stopped at 99 just so that they were the same size, same range. What we're looking at there is what's called the class width. Okay? If we subtract the ending numbers from each other, we should get the same amount over and over and over and over. So 99 minus 89 is 10. 89 minus 79 is 10. Minus 69 is 10. 59 is 10. Okay? So we call that the class width. All right? I've got 10 data values in each class. Sometimes it's not possible to get everything to be exactly the same. It is okay if one or two of the classes are larger or smaller than the rest. If we do that, it should be the first or the last class. All right? So when we look at our grading scale, well, the class for A's usually a little bit bigger because it includes from 90 to 100. The class for F's is usually a lot bigger. It includes 0 to 59. All right? So depending on the data and the usefulness of it, we can adjust the first and the last class accordingly. Okay? But we're going to do the same idea. We're going to look at how many students have scores between 40 and 49. So I see I've got a 47 and a 45 and a 43. Anything else in the 40s? Did I miss anything? No, that looks good. So I've got a frequency of 3. So instead of listing those individually, I list them as a group, anything from 40 to 49. In the 50s, 57, 54, 56, another 57, and a 50, and a 59. Did I miss any of the 50s? I don't think I missed any 50s. So how many 50s is that? 6. Go ahead and finish out the rest of the table. Fine for the 60s, the 70s, the 80s, and the 90s.
Wait, the table, like first, when it says under the class.
So if you look at your standard like grading scale, anything from a 90 to a 100 is an A. Anything from a D9 is a B. These are test scores.
Oh, okay.
No, I was just explaining. So from 40 to 49, if you take the last number in each one, or even the first one, and you subtract them from each subsequent class, you're always going to get that same value. You want the class width for each class to be the same. Otherwise, you're putting. The only exception is if the last or the first one. Sometimes, like, they cut it off at 99 so that it was the same, but it's getting grading scale at 200. So that last class has 11 instead of 10. But you don't want the class that's different with to be. All right. How many students got D's? 6? Okay. How many students got C's? And B's? 9. How many students got A's? 5. Okay. So we see a trend in the data. Most students got C's. Okay. Pretty standard bell curve in there. Again, making sure that this adds up to your frequency number. We knew there were 40 tests, so we want to make sure that all of the frequencies in each row adds up to 40 for the total number of data items. Now, there are a couple different ways of representing data. We're going to use some of those same charts that we already did. We've got a distribution set, histograms, and then frequency polygons after that. A histogram is just another visual way of showing the information that we get from a distribution table, frequency distribution, and it just lets us kind of visually see this trend across the data sets. All right, this was our very first chart that we had on the maximum growth over time. It's the same thing, but instead of having two tables, I've got X and Y axes. X-axis labeled with age, 10, 11, 12, 13, 14, 15 years of age. And then the Y-axis is the frequency, 1, 2, 3, 4, 5, all the way up to 9. And so instead of listing the data values, if I have a frequency of 1, the bar goes up to 1. Frequency of 2, frequency of 5, frequency of 7, 9, and then back down on the list. It just shows us a visual representation. If we've got a frequency distribution table, then a histogram is really easy to make because we just turn these values into bar heights. Same thing with a frequency polygon. That's this graph on the right. If I've already got a frequency distribution or I have a histogram, it's really easy to write the polygon instead, because instead of doing bar heights, I just do dots to represent those different values. Depending on the data, how large the data set is, the variance in the data, different types of displays may be more beneficial. It just varies. So if you end up, whenever you take a more in-depth statistics course, you'll look into all the different ways of describing data and which ones would be most beneficial based on what's given. Last one is a stem and leaf plot. It's a little bit more time consuming to make, but it gives us a better, more holistic picture of our data set. We're going to take those test scores that we did with the frequency distribution, and then we're going to look at the how it looks different in a stem and leaf plot. So the way a stem and leaf plot works is we take the tens place, and that's going to be our stem. 40s, 50s, 60s, 70s, 80s, 90s. That's our stems. The leaves will be the individual ones place, the individual unit digits. So if I had a 47, well, that's going to go 47. Okay? And so you can run down the list with your stems and then fill in your leaves. So we can start at 82 and write a 2 down here. We can fill in a 47, 47. 75, go to the 7, fill in a 5. And then we just keep running down the list. 64, 57. Go ahead and keep filling that in. Go through the list and fill in all the leaves with their corresponding stems. Then write it again. If a number shows up more than once, write it again. So we've got 82, so we're going to write another 2. So when we get our stem and leaf, then we get in all our leaves filled in, you can see it gives us a visual representation similar to our histogram, but what it also does is it preserves the individual data values. So we can still see that we have that type of a curve that we would get with a histogram, but we don't lose the individual values, so we can still analyze within a subgroup. And I can say, okay, well, of the students that got a C, I can see that, well, most of them were 75 and above. So most of the students got a C or a C+. And then we can also compare that, with any of the students that got an A, well, they got an A or an A minus. So I didn't have anything close to the high end. And so when we have a histogram, we lose all the individual values in the middle. All of these that were... Well, it didn't work with that one, but for this one, when we look at our frequency table, if I've lost this data value, because I made a histogram, and I don't know what these are anymore, I just have this information. For all the students that got a C, between 70 and 79, I don't know what their individual data scores are anymore because I lost it when I made the table, because I grouped them all together. So this is a little faster, but we lose some of the information. If we do a stem and leaf plot, it takes a little longer, but it preserves that individual data information. And again, it just depends on what we need and what's going to be most useful for us. Now, from there, now that you know how to create some representations, and we can look at visual representations, we're going to talk about some ways that the data can be deceptive. Okay? So, Benjamin Disraeli, Queen Victoria's Prime Minister a while ago, stated, I talked about this last week, there's lies, there's damn lies, and there's statistics. Okay? Statistics by themselves do not lie. It is just raw data. Okay? It is facts in its purest form. But how that information gets presented, well, that's where the trouble lies in. Okay? And as functioning adults that you're about to be, Lord willing, you will be voting, dear God, and you'll be buying lots and lots of things. And the people that want you to vote for them and the people that want you to buy their stuff are going to be not necessarily lying, some of them will be lying, but they will be using this information to bend the truth to whatever their goal is. And they may have the best intentions in mind. Okay? But you need to be aware of how that information can be misrepresented so that you can make an informed decision about where your money should go or where your vote should go. So I have two different line graphs here showing the U.S. poverty rate over a 5-year period. They both represent this same exact data, but in very different ways. One of them shows a rapid increase in the poverty rate. One shows a slower increase in the poverty rate. What's the difference between these two graphs that's causing that distortion? Yeah, for the y-axis. They're the same values for the data points themselves, but but the range on the y-axis is different. This is a 0.4% increase per tick mark versus a 2% increase per tick mark. So how the data is being presented, it doesn't mean that either of these graphs is wrong. They present the data as it is, but they present it in such a way that you could push one agenda or another. Saying our poverty rate's increasing really quickly, we need to increase social programs. Or, the poverty rate isn't going up very much, we could probably decrease social programs. Okay? Whatever their argument may be. So it's up to you as a consumer, as a voter, as a citizen, to be able to look at the information as it's presented and look at the whole picture. Don't just look at the line, look at the numbers and see what is it telling you. Interpret it on your own. So things to look out for. All right? First of all, is there a title that explains what's being displayed? If you don't know what they're talking about, what good is it going to do? Do the numbers line up? Is the scale clearly indicated? Has the scale been varied to make a more or less dramatic impression than what's actually shown? Okay? Here the scale is adjusted, so it makes a difference. Are there too many designs or cosmetic effects? This shows up a lot. Okay? News articles, magazines, they're trying to get a point across, but they still want it to be attractive, appealing, because they want you to look at it. They got to get your eyeballs on it. Well, if it doesn't look good, well, then you might not look at it. And so they use graphics and designs to try and draw your attention to it, but those same graphics and designs may distort the information that's being given. We'll look at a couple examples of those in a minute. Okay? Has the wrong impression been created by how the data is changing because of either equally spaced time intervals, not used on the horizontal axis? A lot of times you'll see data on a chart, okay, and you've got your x and y axis, but these may not be a consistent interval. It may be, this is a 2-year gap, and this is a 5-year gap, and this is a 1-year gap, and this is a 3-year gap, and this is a 6-year gap. If it's not consistent, then it distorts the information. Are bar sizes scaled proportionally in terms of the data? We'll see some of that. And then this is a big thing, the source. Is there a source that indicates where the data came from? That can be a really big one. All right? A lot of times when you see opinion polls or public approval ratings, those show up all the time. Here's President Biden's approval ratings in the first 100 days of office. Here's his current approval rating. Here's comparing it to other presidents. If you ask Democrats versus Republicans their approval of the president, are they going to have the same approval? No. And so you'll oftentimes see little subheadings. It will say President Biden's approval rating among Democrats or among Republicans, depending on where you see the information. And you'll see it with every single president. We've done it ever since the advent of TV news. Okay? Because they're trying to push an agenda. They all have them. Okay? So you have to look for that information, because if you don't have the whole picture, well, then how can you make an informed decision? So here's just a couple examples, and we'll look at more later in the week, and you'll see some more within your book, of how the graphs are distorting the information that's being shown. So we have this first graph that shows the purchasing power of the diminishing dollar. So over time, the dollar is decreasing in value. Okay? Well, one of the things that's a little frustrating is you've got a 10-year gap here and then 5, 5, 5. Okay? It's not consistent. But also, the biggest issue here is that the volume, or I'm sorry, the volume, the area the dollar takes up is changing. And it has a bigger impact, whether you realize it or not. If you're just glancing at the data, if you're just glancing at the graphic, you have about a 60% decrease in the height, but the area is about 4 times smaller because it's making it skinnier and shorter. And so the change in the area is having a disproportionate impact on representing how the data looks. So if you stripped out the volume and you just look at lines, okay, it's less dramatic of a decline, but the difference in the area is making a larger impression. Is it a good thing? Is it a bad thing? Does it matter? Maybe not. But it's things you need to be aware of. Number of square feet in an average single-family home in the United States. Okay, so we're looking at a 20-year gap versus a 16-year gap or a 14-year gap. Not a huge difference. The big thing is, look at the difference in the housing prices. Or not the housing prices, in the square feet. So from 1,500 to 2,000, that's about 30% more. Okay? And then from 2000 to 23, that's about, I don't know, quick math, around 15%. Why is it so much bigger? This is double the area from the previous one. Okay? So look at the numbers. The graphic is not a proportional representation of the increase in the square footage. Does it look better? Maybe. But does it actually tell you the full picture? No. This was a big one. Stock market crashed on Monday of October 19th, 1987. 500 points. Huge drop. Okay? Lost almost a quarter of its value in a day. Alright? Which has potentials for people's retirements being wiped out, jobs being lost, homes being lost. It's big impact. Okay? So the graph on the left was one that was run in a major newspaper. And what it was talking about is over the 15-year period from 1972 to 1987, the market had a pretty steady increase. It was a little slow for the first half of that 15-year period, and then we had this huge sharp incline, and then they wanted to highlight how drastic the market tanked on that one day. Okay, 15 years of growth wiped out in a day. Do you have something you want to add? That corner, there's a lot of whispering that I'm hearing and giggling. So do you have anything you want to add?
Not at the moment.
That graph is based off of 3 data points. And so that's why this curve gets smoothed out. And it shows that there was good growth over that 15 years. Every day was a good day in the market, more or less. But when you include all the data points for each year, you see a lot of volatility within that market. And it paints an entirely different picture. Yes, overall the trend was good. But in this 2-year period, they lost the same amount. There's a big decline. 500 or more points over a 2-year period. Another couple hundred points in the market over a couple-year period. So there were times of serious economic impact. Where this relates more to you, whether you invest in the stock market or not, okay, which if you ever get a retirement, you give your money to, you have it in a 401k or any type of retirement account, that money is getting invested in the stock market. So being aware of the overall trend. But where this also plays into is when we have good economic times, usually the political powers that are in control maintain control during that time. People don't want to upset the balance. Okay? Jobs are good, wages are going up. Those types of things will affect the sitting president, sitting Congress. But then when there's a crash and the market goes down, well, the people that were in power, some of them lose their jobs. And we put new people in power. And so depending on, you have upcoming elections, well, the market was really good until this president got here, and then it tanked. that might change your opinion on where you vote. So being aware of that type of information and whether or not enough information is being shown is going to have an impact on your decision. Be aware. Sometimes graphs are laughably bad, and they distort the picture completely. And to be aware of that information if you're going to make good decisions. And if you're not going to be aware of that information, then please don't vote. I want you to vote, but I want you to make sure you have all the information. It's really important because the stake of our country is in your hands. If you don't have all the information, then how can you make a good decision? Whether it's about, can you afford to buy a house right now? Or who should we vote into office and who should we vote out? Statistics can lie if written the wrong way. You need to pay attention to how those things can be deceptive.